Okay, so 2.5. I need you to pay close attention to this part because this will be a part that you'll be expected to do without a calculator. And then we'll move into the part where you can use a calculator to actually write exponential functions, okay, as far as doing a regression. But I need you to pay careful attention to this part. And if we need to, we'll go over it in class as well. But I want to make sure you're seeing how this works, okay? So again, not every single set of data, right, is going to look really, really pretty, and you're going to immediately be able to tell what you've multiplied by. And there's a reason. It's because in the real world, you're not just going to get an initial amount and a base or a common ratio. You're going to have vertical translations, right, that make the graph go up and down because it doesn't need to start at, wherever it started, like 0 normal. Okay, so that changes the outputs, right, the f of x values on your function, and it takes a little bit more work to write them. Okay, so I need you to pay careful attention. All right, so 7, 13, 25, 49, 97. Definitely does not look like something, recognizable as far as like where you can look at it and realize what you're multiplying by every single time. Okay, however, we can add or subtract numbers from it, and we would actually be able to see this really, really nice pattern. So if I subtracted 1 from each one of these values, right, from my output values, I would get 6, 12, 24, 48, and 96, which is a very recognizable pattern. You can immediately tell that you're multiplying by 2 every single time, right? 6 times 2 is 12, 12 times 2 is 24, da, 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 da. Okay, so writing the function after that part is very, very easy, okay? I had to subtract 1, right, in order to get it to look recognizable. That means when I write the function, 1 has actually been added. Okay, and you know what the base is because you know what you multiplied every single time, and you also know what your initial value was, 6. So the function can actually be written as 6 times 2 to the x, and then a vertical translation of 1. Right, I had to subtract 1 to recognize the pattern, which means that 1 was added to get the original number. So I want to make sure you're thinking about that really carefully. Okay, so, and if you substitute in your x values, or your input values, you're going to get this actual pattern. 2 to the 0 is 1, 6 plus 1 is 7, 2 to the first is 2, 12 plus 1 is 13. It does actually work. Okay, so again, I'm not seeing a pattern. Okay, so I'm going to try subtracting, and then I'm going to try adding just to see if I can find some numbers that work. So let's say if I subtract 1, I'm going to get 1, 9, 33. I'm still not seeing any kind of recognizable pattern, right? It doesn't look like I could multiply by anything to get there. So let's try adding 1 just to see what that does. Okay, plus 1. That's going to give me 3, 11. No, I can stop there. There's nothing that I can think of that will multiply to get me from 3 to 11. That's not going to be like a whole number base. All right, so if we subtract 2, let's see that. I'm going to get 0, 8, 32. Well, see, that would work. 8 times 4 would be 32, but 0 times nothing is going to give me 8. So that's not going to work. All right, so let's try adding 2 and see if I can find, again, a pattern that will actually show me what I'm doing. All right, so if I add 2, I'm going to get 4, 12, 36, 108, and 324. Now, I'm not really sure without a calculator for the last ones, but I know if I multiply 4 times 3, I get 12, and 12 times 3, I get 36. So I know that my base is going to be 3. Okay, and I know my first term is 4, and then what did I do to the function? Well, I had to add 2 to get it to look like the pattern, which means I must have had to subtract 2 originally for the numbers. So that's always going to be the opposite when you write your actual function, right? If I have to add 2 to find the pattern, that means 2 was subtracted from the original function. All right, so let's try a little bit more complicated one. Now these numbers look like powers, close to powers of 2. So I'm going to go with a bet of adding 1 this time, just because I know I have some powers of 2 that I'm going to deal with. So add 1. So if I add 1, I'm going to get 64, 32, 16, 8, and 4. Yes, definitely powers of 2. But instead of getting bigger, I'm getting smaller, which means technically I divided by 2. So my base is a half. Okay, so here's the question then. My first term is 64, right? So if I had to add 1 to find the pattern, that means the original one had a -1. I hope you caught that. But that's how it works as far as writing those. Okay, so let's move on to ones that you actually get to put into your graphing calculator or into your Desmos. We're going to be doing regressions now with these. Okay, so, and we really only need 2 points. We proved that when we were doing geometric sequences. But, I mean, we could set it up as a geometric sequence where this is g of k, and this is k, and then this is g of n, and this is n. But I don't know about you, but I don't want to solve 20 minus 2. I don't want to solve that. I don't want to take the 18th root of anything, and I don't think 2602 is going to divide evenly by 47. So we're just going to go ahead and do a regression for it. Okay, so we're going to go ahead and put in those 2 points. I've already got the calculator up and ready. So our 2 points are 2 and 47. And then the other one was 20 and 2602. Now, they went ahead and ran it for you in the notes, but I want to go ahead and run it so you can remember how to go through it. So you put your data in. Remember to label your X and your Y column, right, so that we actually have the name for them, right? And then we're going to go into the menu and statistics, stat calculations. We know for a fact already this is exponential, so we're going to do an exponential regression on it. My X list is X. My Y list is Y. Yes, I'm going to save the function just because I want to look at it. In this case, we don't actually have to graph the points because there's only 2 of them. So, okay. And there's my equation. So I can actually write the equation with my initial term and my base. Okay, and if you take a look back at the notes, it is the same thing that they got here. They went ahead and just, put in the data for you. All right, so the equation would be f of t, since that was the variables they gave us. Again, 3 decimals, 3.089. Base is 1. We're going to round that up double. That's a double round up. So 250 to the x power. All right, so not too bad. Again, you're going to be doing this a couple more times just to make sure you can actually run it. And then we'll do a couple more things in the calculator to make sure that you are good to go. Okay. So I'll go ahead and give you some time to set that one up. I'm going to type it into my calculator as well, just to make sure you've got it. But we are going to be finding the values of A and B by putting it in the graphing calculator or Desmos. Now, we talked a little bit about this before, remember how I was saying you have to do arithmetic sequences the way I showed you, where you're treating it like a system of linear equations. This is exactly what I'm talking about when you get a open response question that specifically tells you write 2 equations that can be used to solve. Okay, so keep in mind that it's g of x is your output, right? Okay, and then x is your input value. So it's actually very, very easy. Your first term, your input value is 3, your output value is 21.54. So the first equation is legitimately that. 2154 equals A times some base to the third power. Okay, and then the second equation, 3.62 equals A times B to the 8th. And again, we already know how to do this if it was a geometric sequence, but I'm not dealing with the fifth root of anything. And again, 2154 and 3.62 are not going to divide evenly. Okay. If they had given you some values that could divide evenly, those would be the kinds that you would do without a calculator. Okay, but decimals like this, no. All right, so let's go back to the calculator and put those in. So I'm going to go home. Ask for new. No, I don't want to save. Looking for a spreadsheet. Okay, so the first input is 3, and the second input is 8. First output is 21.54, and then 3.62. Again, make sure you name your variables like we're supposed to. And again, we don't need to graph it when it's only 2 points. You might as well just go ahead and hit menu and run the statistics on it. Oop, that was not what I wanted. Cancel. I was trying to see what else was on there. Okay, so statistics. Okay, so we have logarithmic and sinusoidal and logistic. Oh, goodness. Okay, just wanted to see what was else on there. So exponential regression, most definitely. And again, your first variable is your x. Your second variable is your y. Okay, equation is done. And we are going to round to 3 places as far as what your values for A and B are. All right, so the actual equation, find the values of A and B. A was 62.801, and I have no doubt if you put this in Desmos, it would have come up with the same thing. If you're curious on how to write it in there, remember that it is y1 approximately A, B raised to the x1, right? You're giving the 2 variables that you want it to find using the points given in your table. Okay, so, and then B, again, is going to be another double roundup, so that is 0.700. Okay, so we do have one more specific base that we're going to deal with, and that is the natural base E. Most of these will be done in a calculator because this is not something that you want to deal with as far as the decimal, right? But it is used, it's used in a lot of places, specifically in science as far as like they're talking about with bacteria cultures. I don't think it's used in carbon dating all that much. Okay, so very, very easy question. Please do not overthink these. So they're going to rewrite this function as basically a base or an initial amount times a base to a t. It's as easy as you think. A is your initial value. A is 17, period. That doesn't change no matter what you put in front of the t. Okay? Don't think about it like you're going to have to rewrite it and it's e to the 0.31 times e to the t. No, you don't have to do that for these type of functions. Your initial value is 17, period. Okay, so we want the average rate of change from 1 to 17. I'm going to go back to my calculator because I'm actually going to put this function in and get the values from there to make my life easier. So, and that's what you'd be expected to do as well. I'll tell you what, I'm going to go ahead and graph it. And it is 17. E is already on the calculator, already automatically comes with an exponent that you need to fill in. And just remember that you hit enter. After that's done, here we go. Just move that over a little bit so I can actually see it. Okay, so it's asking for the average rate of change between 1 and 7 hours. So if you remember, I can get a table, right, of my graph, where I can substitute or look for any numbers that I want. So I have my 7, which is 148.891, right? I'm going to just write that down on my notes just so I'm not going loopy. All right, so 148.891 minus, and then the value at 1, 23.178. 23.178, and then obviously over 7 minus 1, which is just 6. So I need to get my decimal value first, right? So let's just go ahead and do that. I need to add a page, which is just a calculator. All right, so 148.891, 148.891 minus 23.178. 23.178. Get that answer, divide it by 6, and my average rate of change is 20.952. Okay, so find the value of T when the number of bacteria in the particular culture is 1,000. So we're looking for a time when the bacteria culture gets to 1,000. And again, going straight back to the calculator, straight back to the graph. Remember that we can trace points on there. We just have to hit menu and trace, graph trace. Oh, nope, let's try that again. Wrong trace. All right, so menu, trace. I think it was trace all, maybe. I should be able to actually move it at this point. I don't know why it's giving me a hard time. No, I did not want to mess with that. What in the world? Oh, my calculator is being weird. Okay, so go back up, and I did not want to mess with that and change my function. That's supposed to be 0.31. Okay, so I do not want to scroll all the way to 1,000, or rather, actually, I want an output of 1,000, not an input of 1,000. Okay, so if I'm not mistaken, there was a trace where we could actually type in a number. I remember this. Hang on. Graph trace. Okay. Should be a one where you can actually put in a value. I know there's a way to do it. You know what? I'm just going to graph another function to see where they actually meet. Should be another function on there. See, I haven't gotten high enough yet. It's only at 120. All right, so menu. Nope. Oh, zoom. That's not what I wanted. Menu. Let's try that again. Zoom. Out. Nope. Still not. Menu. Zoom. Out again. Getting close. There we go. Now I've actually found where they meet. All right. So what I need is the intersection point. Oh, this would be so much easier on Desmos. So menu, let's see. How about analyze? Intersection. There we go. That one and that one. Oop, let's try that again. Menu, analyze, intersection, there to there. There we go. So it's telling me that it reaches 1,000. Oh, we'll go over that in class with more if we need to. But it's telling me it reaches 1,000 at 13 point something years. I believe that was supposed to be years, right? No, sorry, 13 point something hours. So we will go over that some more. And then also, again, in Desmos, it would be easier. But for right now, we're just going to say 13.1 hours. There's also a way to solve that algebraically on a calculator, and I will show you that one as well. Okay, so that was fun. All right, so for the last one, again, very, very basic, although we will be using the calculator for this one too. Okay, so find the values of A, B, and use the values to write an expression. Okay, well, A is just your initial value. That's 50. If it's increasing by 13% every year, this is going way back to Algebra 1 as far as writing exponential growth. So the actual function would be 50 times 1.13 to the t. Okay, and then the second one's very, very easy. You're just plugging in 6 years for t. So 1.13 raised to the 6th power. Again, back to the calculator. And I'm just going to go back to my actual calculator portion of it. So 50 times 1.13 close raised to the 6th power. Okay, 104.098 deer. And since we don't do partial animals or partial people, because that's gross, we're just going to say it's 104 deer. Okay, same thing. We want it to be able to reach 5,000. So you're going to basically, you're looking for an output where the input is, or you're looking for rather for an input where your output is 5,000. Again, I'll show you tomorrow how to actually do this algebraically. It's not all that bad. It's one of those things, if you remember back from Algebra 2, as far as using logs and exponents, the actual answer in time would be 37.68 years. Okay, so as far as going into the calculator to actually solve it by graphing. Okay, and again, you can do that in Desmos as well, where you graph the right side as one equation, the left side as one equation, and you're looking for their intersection. Okay, so this one has to do with being able to rewrite your exponents. Okay, so if t is measured in months instead of years, this is how the function is going to look. Okay, so 50, 1.13, t divided by 12. And that's the only difference. If you were originally given this in months and they told you to measure it in years, then you would be multiplying 12t, because 12 months would equal 1 year. If you're, again, it's still 13% per year, you're now measuring it in months. That means each month is basically 1/12 of a year. So that's why that works that way. And it's based on the fact that your percentage rate is based on years, even if you're measuring in months. Okay, so that is it for 2.5, and I will see y'all later.